Hello again, gang. Mr. Cruze here with a probability and statistics lesson for you. Today we're going to talk a little correlation. Again, I do apologize for not being there. I'm at a iStep workshop. I hope you're being good for the sub. All I ask is that you watch this video, fill out the notes, and work on the homework, all right? Your 3.1 and 3.2 worksheets both are going to be due in class tomorrow. So make sure you get both of those done today. You should have plenty of time. So yesterday we talked about how a scatter plot talks about three things. You know, when we plot two quantitative variables, it gives us the form, the direction, and the strength, right? You know, we can talk about, is it linear or nonlinear? Is it positive or negative? How strong is it? The real problem is that strength one. You know, what you say is moderately strong, I might say is moderately weak, and vice versa. So obviously our eyes are probably not the best judges of that sort of thing. So we need an actual numerical measure, and that is what is known as correlation. Now, correlation, we usually use the letter R to represent it, but all correlation does is it measures the direction and strength, so it does tell you both direction and strength of the linear relationship, okay? Very important here, is only for linear relationships, not quadratic or exponential or any other sort of relationships that you might come across, but we're only going to do linear in here, between two quantitative variables. All right, and they do have to be quantitative variables. I don't know if you've heard me ever say it or anything, but usually I hear people say, oh, there's a correlation between like what gender you are and what party you vote for. And it's like, no. Those are not quantitative variables. Hair color, gender and hair color and things like that, you don't say there's a correlation between them. You might say there's an association, but not a correlation. Because correlation is a numerical measure, and you can't do numerical measures for categories. All right? But anyway, that's neither here nor there. It measures the direction and strength. So, a couple pieces of information here regarding correlation. First, it makes no difference which variable you call x and which one you call y. As far as yesterday, we talked about explanatory and response variables. Doesn't matter, correlation doesn't care, but both variables must be quantitative. If they're not quantitative, you can't calculate correlation. Another cool thing about correlation, this is why there's no difference between x and y, correlation has no unit of measurement. It's just a number, no unit at all. Very similar to some other things that we've talked about before, but like z-scores and things like that, but no unit of measurement, it's just a number. Therefore, R doesn't change if you change the units onto X, Y, or both. So, if I have a bunch of temperature readings and they're in Fahrenheit, and I turn them all to Celsius, it doesn't matter. The correlation would still stay the same. Okay. One of the things I talked about is it measures direction. A positive R indicates, obviously, a positive association between the two variables. And a negative R indicates, obviously, a negative association. Okay, the closer it is to 0, obviously, not very strong. R will always be a number between -1 and 1. It can't go outside of that. So if anybody ever tells you, oh, I got a correlation of like 5, they're doing something wrong. You cannot get a correlation outside of -1 and 1. Values of R near 0 indicate a very weak linear relationship. Either side, doesn't matter if it's positive or negative. Okay? But the strength increases the farther it gets away from 0 and the closer it gets to either -1 or 1. I want to be very clear about this. Even negative relationships can be strong ones. They would just be strong negative relationships. Obviously, the extreme values -1 and 1, that only occurs in the case of a perfect linear relationship. Like they would literally make a perfect algebra line. Okay? Just kind of keeping that in mind. Correlation measures strength of only a linear relationship. I already mentioned that. No curves. All right, so if your data curves, you probably should not be calculating correlation for it. So I'm just going to jot this off to the side. No curves. And then correlation, because it uses every data value, is not resistant to outliers, just like mean, standard deviation, all that good stuff. It is affected by outliers. It easily changes if there is an outlier. Okay, now, how do I actually calculate correlation? To be honest, there's a big scary formula. We're not going to use that in this class. We're actually going to use our calculators. So one of the things, I think I had you guys do this before, but just in case you haven't, let me turn on my calculator here. One of the things I had you guys do is I had you hit second catalog, and you hit this X to the negative first button, the D button, and it takes you down to D, and then you arrow down to diagnostic on. You only have to do this the first time. Okay, once you hit that, it is on, good forever. Don't reset your calculator. It will now do what you need it to do. Okay, but what we're going to do, we'll do this with some data here in a second. You're going to put data into your list. So you hit Stat, Edit. You notice I've got some numbers here. I'm going to clear those out. But basically what we're going to do is we're going to put our X values in one list, our Y values in the other, and we're going to make it calculate correlation that way. All right. And I'm going to show you how to do that here in a second. Okay, so a couple other pieces of information that just to clarify things and make sure it's all in one spot. R is always between -1 and 1. I can't stress that enough. If it's R is greater than 0, we say it's positively associated. Okay, a positive correlation indicates a positive association. Obviously, if it's negative, then that is a negative association, negatively associated. If R equals 1 exactly, that is a perfect positive relationship. I will tell you, if you're using real data, it's very difficult to get a perfect positive relationship. In fact, if you did, I'd probably be a little suspicious of your data. Obviously, the closer you get to 1 indicates a strong positive relationship, a stronger positive relationship. So if you get like an R value of like 0.7 versus an R value of like 0.9, obviously the 0.9 would be stronger. -1 is the opposite of that. It's a perfect negative relationship. It would just be a perfectly sloping negative line. Okay, and again, the closer you get to -1, indicates a stronger negative relationship. And I do apologize, I'm writing so quickly. I just want to make sure that we have plenty of time to get all this in. Obviously, if you need to slow down the video and rewind it or pause it, something like that, please do. Okay. And then the other case that we like to talk about is R equals 0, and that indicates no linear relationship. If you get 0, there's pretty much nothing there. Nothing special. All right, let's actually try one. So no context here. I'm just going to give you a set of ordered pairs here. So like this is an ordered pair, this is an ordered pair, and so on. What you're going to do is you're going to grab your handy-dandy calculator, and we're going to type these in. So I'm going to type in the X values first. So 10, 12, 14, 16. I'm looking at paper off to the side. So 18 and 20 are the last two. So there's 6 apparently. And then I'm going to go to L2, and I'm going to type in my Y values. So 1.8 goes with 10, right? 1.7, 1.5, 1.4, 1, and 0.7. Okay, so what we're going to do is first is have our calculator find R for us. To do so, you simply hit Stat. It's the big button we're going to use a lot in here. Arrow to the right to Calc. You might remember 1var stats. That was something we used before. We're actually going to use option 4 this time. Linreg, linear regression. This is a line, AX plus B. And hit Enter. It will default, by the way, to list 1 and list 2. If you want to tell it a different list, you would just do like L1, comma, L2. But the default is L1 and L2. Anyway, it gives you A and B. That's like your slope and your intercept. We're not worried about that in this class. If you were interested, maybe you should take an AP stats or something. But anyway, we don't care about R squared in this class, but we do care about R. It's the bottom one there. Our R value is negative 0.97. We're going to go 3 places. Negative 0.973. 973. Okay, so the first thing we're going to do is use that number. Tell us if it's positively or negatively associated. Well, obviously, the number is negative, so it is a negative association. And if you were to plot the graph, not that you have to, you would see that as x increases, y decreases, and that would be negative relationship. Now, how strong is it? Basically, how close is this number to -1? I'd say it's pretty darn close. So that is a very strong negative relationship. It is almost -1. And that's pretty much it. You're just going to kind of use your calculator for this. You just type the numbers in. Don't forget to clear out data. You arrow up and then hit clear and then arrow back down, and that'll clear out your list. That way you don't hit delete or anything like that. But it's pretty much just type it in and then using that option for Linreg AX plus B. Okay. I hope this has helped. Obviously, if you have questions, feel free to message me on Canvas. Feel free to email me or anything like that. I will be checking my phone, so please get a hold of me if you have questions. Other than that, have a wonderful day. Make sure you work on your homework, and I will see you tomorrow. Peace out.